afternoon and welcome to my talk. This talk is about the Java Cloud Native stack for microservices and serverless architecture. And this is a kind of like big overview or introduction about the basics. And it's because I created this talk because in the past I was very confused about all of these buzzwords. What is cloud native actually, microservices, serverless, and so on. So I talked to many people, asked some stupid questions, and created a talk. So my name is Markus Kett. I'm CEO and co-founder of MicroStream, and I started with Java almost more than 20 years ago, and worked with my team on a Java development environment based on Java Swing. Then we migrated everything to Eclipse. We worked many years on the JBoss Hibernate tools. So we worked on improving the JBoss Hibernate tools. And then we open sourced libraries. We created JPA-SQL, which is a JPA criteria-based query language for Java. And then we started the MicroStream project, which is now Eclipse Store. This is a little bit about my background. So the cloud changed everything, and it changed the way we develop software. It started with conventional data centers and ended up with the cloud. So computing resources in the cloud, on demand, endless scalable hardware, infrastructure as code, so getting new computing power or storage resources just by writing some lines of code. This was really revolutionary. Computing power on demand, very easily scaling vertically and horizontally, fully managed services, and the pay-as-you-go model. And of course, software as a service. This altogether revolutionized the way we build software, the way we sell software, almost everything. So it started with virtual machines. So it allows us to share server resources. And then the next level of revolution was container with Docker, of course, and then microservices. But actually, what is a microservice? Who of you develops microservices? Okay, quite a few. So the plan here, or the concept, is cutting a monolithic application into multiple smaller services. And all of these services should run in their own container, that you'll be able to develop, test, and deploy all of these services isolated from each other, and run all of these services on a container platform that cares for almost everything, cares for the resources, cares for vertically scaling and horizontally scaling. The question is, what actually is cloud native? So there might be very different definitions. So what I've learned is it is software architecture that is designed and optimized for the cloud, for cloud computing environments. So, using cloud technologies and principles provided by the cloud vendor. For instance, PostgreSQL as a service. This would be cloud native service. What about, I want to save cloud costs, which means I take I'm sorry for that. The latency is really bad, and with MicroStream actually we work on eliminating latencies. So can we switch it off? So this is a kind of like cloud native service that eliminates the latency. Perfect. So, thank you so much. Now I feel more free. So, what about saving cloud costs by I run my own computing instances and install my database for my own, and I care for managing for my own. Yeah, you can do that, but this is not cloud native. So, and of course we should avoid this because then we have to care for everything. We have to care for security, updates, all this DevOps stuff. And the cloud provider, they care for that. So this is cloud native. And so the approach is use everything that is provided by the cloud. Then you will save a lot of effort, DevOps effort, and in the end costs of infrastructure, and you pay only for what you're really using. And in addition to that, cloud native means you use microservices, which means actually running a monolithic application in the cloud should not be really cloud native. I'm not sure, so it depends, because now we talk about the return of monolithic applications. In my perspective, running monolithic applications, this is okay. With AI machine learning, we very often use monolithic applications again. And of course, running all of these services in their own container, this absolutely makes sense, of course. And it also changed the way we test and deploy the services. And also, it should be scalable. So it should be vertically scalable by the cloud environment. So just adding more computing power, more CPU power or memory if needed. And also scaling the application or the services horizontally. And the goal is always faster time to market, saving cost and effort. But with the cloud and microservices, there are some challenges. And some years ago, when I heard for the very first time about cloud computing microservices, there were these discussions. Is Java really suited for cloud native and for microservices? So is Java really fast, still fast enough for the new cloud age? And many people said no. So now we write microservices with Node.js or Go or something like that. The question is, why were we talking about is Java really suited for cloud native development? And it's because of the traditional Java stack. So when we talk about microservices, there are some rules, kind of like rules. For instance, a microservice should be responsible for only specific task. So build your services for kind of like separation of concerns. It should be small. I didn't find a definition that tells me what is actually small, what actually is micro. Okay, then it should be run in its own container, obviously, and and it should run on a, because it's a microservice, should run on a small machine, so it makes no sense to run microservice on a big machine, of course, so it should run on a micro machine. And you should consider that your microservices can crash all the time, or any time, and which means you have to care for fast restart your services, and because you run it in a small environment, in a small container, in a small machine, we need low memory consumption. And one interesting point is it should have its own database. So a microservice that deals with data should actually have its own database. This is really tricky. So does this mean we want to set up hundreds of server databases? Can be challenging. So the traditional Java stack is built for monolithic applications, of course, because when Java was invented, then we had these monolithic applications. So we had these application servers, and the concept of application servers was, you can install your application server on a big machine, and then your Java applications can share the resources. So of course we had high memory consumption, it was heavy wide, slow startup time, but we were able to share the resources, which means we can save costs, we can save effort, so great concept. But in terms of microservices, do you want to run your microservice in an application server? So this is also challenging. So because of startup time would be really slow, and the effort is very high. Then we also saw some challenges with the JVM itself, because the JVM is very fast because of its JIT compiler, but it's only fast when it's hot. So when the JIT compiler does all these optimizations. But when you start the JVM, then we have latencies. So, but the JVM vendors, they say no, it's not the JVM that it's slow. JVM is fast. It will start very fast. What is slow is your code, because the code has to be optimized, and the JIT compiler has to be warmed up, and this is the latency, of course. But as soon as your code is optimized, then the Java application is almost as fast as a C program. But startup time can be challenging. And what's about traditional Java persistence? So which means each microservice should have its own database, can be challenging. Then in Java we are used to use, when we use a relational database, then we are used to use an object-relational mapping framework like Hibernate. Should we really use Hibernate or other object-relational mapping frameworks in each microservice? So this is also challenging. Is overhead, is this really suited for microservices? It depends, of course. And databases as service are really expensive in the cloud. This is also challenging. From application server to microservice frameworks, this was the next milestone. So first revolution was virtual machines, then containers, and now microservice frameworks, of course. The microservice frameworks changed everything, because now we are able to run a Java runtime within a container, in a single container, and it's a kind like, so David, please correct me, it's a kind like application server built for executing only one single microservice. that runs containerized in your container. So here's an overview. We have these both worlds, Java Enterprise Edition, which is now Jakarta EE, of course. We have all these application servers, and the other world is Spring. Who of you uses application server still? Okay, all the others don't using microservices, obviously use Java SE. Who of you uses Spring? Okay. So now we have all these microservice frameworks, and we have 2 categories, so to say. We have these micro-profile compatible microservice frameworks, and for instance, Open Liberty, Payara, and Helidon. And Helidon here is very special because it's the only framework that provides actually 2 frameworks in one framework. And because we have other frameworks, they do not follow the micro-profile standard. And for instance, Micronaut or Helidon SE. And so with Helidon, you can really do both. Follow the standard or using reactive programming, and these frameworks are optimized for performance, and the goal is to be as fast as possible and to be as lightweight as possible. And with Spring, of course, we have Spring Boot, and this is the big landscape. From the JVM to native images, this is a very important revolution, and I guess this was the big game changer. GraalVM native images, or GraalVM itself, allows you polyglot programming. Who uses GraalVM, by the way? Okay, for polyglot programming? No one. So, okay. So it's more interesting to use GraalVM for native images, obviously. And these numbers are from Oracle. 50x faster startup time, and 5x lower memory footprint, and this sounds great. So this changed everything, and now we were able to build microservices with Java, running Java in cloud-native environments, and this is the big game changer, because now we have the combination of our great Java programming language that is much better than everything else on the market, and it's also really fast, and we can compete with all of these other programming languages. We are better. So great news. But with GraalVM native images, there are also some limitations. We have talks at JCon about this. Yeah, GraalVM native images stuff. So I don't want to jump into deep. And also with testing an executable and deploying, this is a little bit challenging, of course. But we have also great frameworks in the Java community, in the Java ecosystem, where GraalVM native images or GraalVM is supported. So you get support for GraalVM by frameworks like Helidon or Quarkus, so that it's much easier to use the power of this technology. And there's also something very interesting happening in the Java community. There is a OpenJDK project called Crack, and this enables to create a snapshot of your JIT compiler state. So after the functional principle is easy. So JIT compiler is fast as soon as it has optimized your code, and then you can create a snapshot of your state, of your JIT compiler state of the optimization, and can store it persistently on disk. And if you're microservice crashes and you restart the service, then you can load the snapshot and you can restore the state of the optimization, and then JIT compiler don't have to wait for this warm up, and so you can start your service much faster. So JVMs are already supporting OpenJDK Project Crack. Oracle does, as I know, Oracle does not support this feature, and it's because it does not run on all platforms. So this is the reason. So I've heard this is the reason. But you can use it. Otherwise, use GraalVM native images. So in any case, Java is now definitely fast enough. So it's also very important information for customers, obviously. So customers often have concerns about using Java, or it can happen. Then you can say, yes, Java of course is fast enough and much more powerful. So we're absolutely in the game. Then what's about serverless computing? The idea of serverless computing is that we are able to deploy our services, of course, in a container, but we don't want to get in contact with the container platform. So we don't want to care for deciding how much memory do we need, or computing resources, configuration of our environment. So, and this is the idea of serverless. Just give me a container, I deploy my microservice, and care for scaling. So I don't want to care for scaling. The environment should care for scaling. So the cloud computing or the serverless computing platform cares for everything. So the only thing is I have to be able to pay it. So it's an event-driven design platform. So when we call a microservice, then the serverless function will execute your code and will shut down. So this is the functional principle. And it's a pay-as-you-go model, so that's great. So we can save a lot of money. What about traditional persistence and with cloud-native applications? I mentioned already with databases might be a problem with cloud-native, and the reason for that is managed databases are very expensive, and also object-relational mapping within a microservice is effortful. It decreases the complexity. It was okay for it's great for monolithic applications. A monolithic application caring for everything, having one big database, querying a database server, that's great. But if you have hundreds of services and you want to use object-relational mapping, so this might be overkill. And what's the problem here? It's because in Java we deal with objects, and when we try to store data in a relational database, then there is a problem. It's because of these impedance mismatches here. So it's not possible to store just all Java types, all object models, one-to-one in the relational database. So it's because the object model is much more granular than the relational model. You cannot use inheritance. Then in the relational model, for instance, we need this foreign now I'm forget the word. Sorry for that. It's also with this one-to-n relations, this synthetic foreign key constraints. it's because the object model, they have the internal object IDs, they are connected by these object IDs, so this is very easy. And also searching an object model, an object graph in memory is very easy in terms of searching by object IDs, or they are connected. And this is not possible in a relational model, so we need a query language like SQL. And also data types are very different. While we have in Java only hand-off primitive types, in relational database mostly we have 30, 40 or even more data types. And so it's always how can we map and how can we deal with these completely different technologies. And of course, we have these new NoSQL databases. We can choose now document-based database, key value, or graph database. But all of these databases, they provide their own data structure or format. So they have all their specific data formats. And this is very interesting. It's because in Java, we are really able to do everything. And we can just store a simple list or super complex graph in memory. Everything is possible with Java. The database is not. So because there are some databases, they are really focused on a specific use case, like storing simple data, like time series. And the vendors would say, oh, if you have complex data, please don't use it for complex data. So if you have sensor data, then it's built for it. Great. And vice versa, probably the graph database vendors would say, if you have specific use cases, like if you want to store sensor data, graph database might be overkill. So this is the reason why we always have to consider which database actually we want to use for which use case. And we also cannot store our object model one-to-one in these NoSQL databases. So we need in between kind of like mapping or data conversion through every single read and write. And this is very expensive. This is where the latencies come from. No matter which database you use, you can use an in-memory database, for instance. It can be very fast because it's executed in memory, but it don't gives you Java objects, right? So, and if you generate the objects, then you have these latencies, even if you have an in-memory database. And mostly, it will double your query time just for generating the objects. So this problem, this is well known, of course. Impedance mismatch. You can read about on Wikipedia or other sources. This problem is well known. And because of these latencies, because it doubles or sometimes triples your query time, your application gets slow, and probably this is the reason why potential customers often say, oh, Java is very slow, and since we have now this application written in Java, everything is so slow. Yeah, but it's no problem because we are used to use caches. So we can add a cache. And it's great because now we don't hit the database. If a query is already executed, then the results that can be stored in a cache, and then we can just fed the data from a local cache. Have you ever measured how long it takes to read data from a local cache? I expected it would take just some microseconds because I read data from a cache. Cache means in memory. In memory computing means super fast. Microseconds or sometimes nanoseconds, but it's not. So mostly when we measured just reading data from a Hibernate second level cache, it took milliseconds. and we were wondering why. So because we want to provide a very fast development environment, and so the reason is why the objects are serialized into the cache and has to be deserialized when you fetch data from the cache. So and this is also expansive latency. It accelerates, of course, your application, but it's not super fast. So it's okay. So it's common, and EH cache is very common here, and or memcached. Who of you uses distributed applications? Okay, yeah, also common. With distributed applications, and of course you want to scale your microservices horizontally, and because your service is small, it should run on a small machine, which means if the load goes up, then you need more computing power. So the cloud platform should start further nodes of your microservice. It has to scale horizontally. If you use local cache here, then this might be a problem, because if you change data on one node and you store data, then it's in sync with the database. That's great, but the data are not in sync. The data stored in the database are not in sync with all the other nodes. So this might be a problem. But there are so many different cache strategies that we can solve that. So it's common to put the cache between the application nodes and the database. And in cloud, so cloud native should avoid single point of failures, of course. It should be high available, which means it's better to run a cache on multiple machines. Then we talk about the distributed cache. Who uses distributed caches? No one? Okay. Yeah. So in terms of higher loads on the database, this architecture is now great, so it's fast. We talk about distributed cache. Caching is fast, but it's not as fast as we would expect, because the cache is replicated through multiple machines. We have wire in between, and so this is not as fast as fetching data from the memory, of course. But this was an aspect that confuses me, because yeah, I thought, okay, cache means data are in memory, and they are in memory, but the cache runs on a different machine. So keep that in mind. If the load goes up on a database side, then we also are used to put more resources in our database, of course. So it makes no sense to save memory running probably Oracle database with 1 GB memory to save memory. No, so you should have a little bit more memory, of course. But you also need probably replication, because if in a cloud you should be all services should be high available, which means, okay, you need at least 2 instances of your service. So you should have at least 2 copies of your database running in parallel, or even more. When you have a look at the database server, then it looks like a monolithic application. For me, in my perspective, this is a monolithic architecture. Otherwise, you should have hundreds of small database machines. So, in my perspective, it's not the case. So, we have replication. We replicate our database through some database machines. But this is a common architecture. So, which means now we have 3 clusters running, a lot of machines, a lot of memory. And in some cases, the performance is still not good enough, which forces organizations to use search servers, and then they use additional searching servers. Who uses searching servers? By the way, no one. Elasticsearch. So it is also common. They are very successful with searching servers. And then you have 4 clusters running, a lot of effort. So as long as you use all these cloud native functions provided by the cloud vendor, everything is cloud native. That's great. If not, you have a lot of dev effort building up such an architecture. The cloud vendors now provide binary data storages, like AWS S3. It's an object store. It's a binary store. It's probably built for storing photos, PDFs, something like that. But it's also common to use it for storing metadata. And the interesting thing is, in comparison to a database as a service, it's super cheap. Let's say we need 250 gigabyte database with PostgreSQL as a service at AWS, and a small machine costs around $8,800 per year just for one database node. The prices are similar at the other cloud vendors. If you need more replicas, the price will double, will triple. And for instance, when we run 6 nodes, then we pay around $50,000 annually. If we need 250 gigabyte object storage, and it's because I see Wolfgang here, I have to mention Oracle Cloud does offer pretty much the same. Of course, it's called Oracle Object Storage. Costs you only $70 per year. So 50,000 or $70, that's crazy. So why is this so cheap? And can we use this? And the good thing here is it's fully managed by the cloud provider. So they care for backups, for uptime. They guarantee you more than 99% uptime. Data center replication also. You don't have to care for anything. And we can combine this now with Java, with the power of Java, and we can make it simple, more simple. And Java is very fast. Everything that's executed in memory, we will talk about microsecond response time. And we have a great data structure. So the database vendors, they provide their specific data structure, and now they want to create these multi-model databases, because they also recognized that the microservices should be responsible for a specific task, and so the microservice infrastructure need multiple and different data structure. So they also create now, or try to create, multi-model databases. But in Java we have a multi-model model, a multi-data model from the beginning, because we have object graph, we have collections, we can store simple lists, we can also create a very complex object graph. Everything is possible in Java. So we have a multi-model data structure from the beginning, and we can search with Java streams on an object graph in microseconds. So if you even have 20 terabyte memory, and you have 20 terabyte data in memory, and a very complex graph structure with millions of nodes in your graph, then you can search it in microseconds with Java Streams API. And it's, by the way, type safe, fully object oriented. That's great. And here we talk about microsecond response time. And it's the pure power of the JVM. Everything executed in memory. The only thing missing was so far persistence. And with the Eclipse Store, we now provide persistence for Java. And the concept is system prevalence. Just keep the functional principle is simple. Keep your data in memory, or just load data in memory you really need. And this fits great to serverless functions. And then for storing the data persistently on disk, just create a snapshot. And we do here pretty much the same as project OpenJDK project Crack does. So they use snapshots for creating, for storing the optimized state of the JIT compiler, and you can do pretty much the same with data, with application data, by using this functional principle. Just create a snapshot, and with the new Eclipse project, Eclipse Store, we can now do this with application data. Eclipse Store in a nutshell is a Java native micropersistence layer that fits great with microservices and serverless functions. And it allows you to store any kind of objects, any complexity, into any binary data store. You can store it on persistent volumes. You can store it in the cloud object store, and you can store it even in a database, because databases are also able to store binaries. Vice versa, it allows you to load any object references from the storage when it's needed. You can load single subgraphs into the memory and restore the object graph in memory, or only some subgraphs in memory when needed. The framework is open source. It's already integrated with project Helidon. It's built for microservices and fits great with microservices. And you can see the architecture is very simple. So you just need your data in memory, your objects in memory. We need a virtual machine or a native GraalVM native image, so it runs also on native images. And you need a data storage. So as I mentioned, object storage is perfect for that because it's fully managed. And it's super fast because everything is executed in memory, microsecond response time, and when you store data persistently, you save 98% data storage costs in the cloud. And a good thing for developers is this concept is fully core Java, only core Java concepts, no database specific concepts, and you can do whatever you like in Java. It can be stored by Eclipse Store. And then we can have a look on our huge architecture, and now we can replace the application or the microservice nodes with Eclipse Store nodes. And now magic happens. We keep data in memory, and with the Eclipse Store cluster we are able to replicate the system state through multiple JVM processes. So, which means data are already in memory. We use it as an in-memory database. We don't need local caches anymore, and we don't need a distributed cache anymore because it works already like a distributed cache. And because we store data in a binary data store in the cloud, it's fully managed data center application and so on. We don't need a database cluster anymore. So you can skip the database cluster, which is probably most expensive. We can skip the distributed cache, and the end result is a very slim architecture, very cheap architecture, core Java. Everything is core Java. No requirements to your classes. That's the good thing here. If you use Eclipse Store, then you don't have to use interfaces where you have to implement like serializable. There are no interfaces to implement, no annotations, no superclasses, just POJOs. You can create your object model completely freely. You don't have to build your object model around the database model or that it fits for your database. So very easy to use. And when we use replication, of course, then we replicate the state, then these nodes will be stateful, but with REST, for instance, we can also run serverless functions and query the Eclipse Store cluster by using REST. And then you can also build serverless functions, use it with serverless function, and then you can also use Python, for instance, or .NET. That's very popular at Java conferences. So, conclusion, Java Cloud Native infrastructure. Java is built for the cloud, and it's great for the cloud because now we have Graalvm native images. It accelerates Java tremendously. We have microservice frameworks like Helidon as a runtime for your microservice written in Java. You have Eclipse Store for persisting your data, very lightweight persistence, very cheap persistence. It's built for executing your Java stack on container platforms or serverless platforms, and you can use binary data storages to store your data persistently on disk. Everything is cloud native, and you save 98% database cost in the cloud. This is the new Java stack, the new Java Cloud Native stack for serverless applications and microservices. Or it can, so it can be. This is only an option for you guys. Of course, check it out. You have to use what fits best for use case and best for your team, for your yeah. What's best for you? The Java ecosystem is very strong and provides a lot of solutions. But the great answer is we can solve all use cases, and Java also is ready for machine learning, by the way. So this is the future, and probably we'll have a lot of more talks in the upcoming years about this topic, and Java is also great for this use case. If you have questions about Eclipse Store, can check this out. It's free, and the very first final, it's not final, the very first release is now available. It's the milestone 1 release, and in some weeks we will have the final release. All right, thanks for coming, and if you have further question, yeah, you can find us on the Eclipse Store booth. Thank you so much.